Introduction. Analyze and implement fundamental neural network architectures including feed-forward, convolutional, CNNs, and recurrent neural networks, RNNs, understanding their specific applications and limitations. Welcome to this session where you will learn about key neural network types. We will explore how to build and use feed-forward networks, CNNs, and RNNs for different tasks. Understanding feed-forward neural networks. Feed-forward networks are the simplest type of neural networks. Data flows in one direction from input to output layers. They are used for general prediction and classification tasks where data points are independent of each other. Understanding convolutional neural networks, CNNs. CNNs specialize in processing grid-like data such as images. They use convolutional layers to detect patterns like edges, shapes, and textures. CNNs excel in image recognition, object detection, and similar tasks. Understanding recurrent neural networks, RNNs. RNNs handle sequential data by maintaining internal memory of previous inputs. They are ideal for time series analysis, natural language processing, and speech recognition, where past context influences predictions. Applications of feed-forward networks. These networks work well for tabular data and straightforward classification problems. They are easy to implement and require less computational power compared to CNNs or RNNs. Applications of CNNs. CNNs are widely used in computer vision tasks like facial recognition, medical imaging, and autonomous driving. Their architecture enables them to learn spatial hierarchies and data efficiently. Applications of RNNs. RNNs are suited for tasks involving sequences such as language translation, sentiment analysis, and speech synthesis. They can model temporal dependencies that feed-forward networks cannot. Limitations of feed-forward networks. They cannot capture temporal or spatial dependencies in data. This makes them less effective for sequences or structured inputs like images or text. Limitations of CNNs. CNNs require large amounts of labeled image data and substantial computing resources. They are not designed for sequential data processing. Limitations of RNNs. RNNs can suffer from vanishing or exploding gradients, making training difficult for long sequences. Variants like LSTM and GRU address some of these issues. Implementing neural network architectures. Start by selecting the appropriate architecture based on your data type and task. Use frameworks like TensorFlow or PyTorch to build and train your models. Test each model thoroughly on relevant datasets. Real-world example using CNNs. In medical imaging, CNNs help detect tumors by learning to recognize patterns in MRI scans. This automates diagnosis and improves accuracy. Real-world example using RNNs. In language modeling, RNNs generate text by predicting the next word in a sequence, enabling applications like chatbots and translators. Reflecting on your projects. Consider the types of data you work with. Which neural network architecture fits best? How can understanding limitations improve your model choices? Best practices for neural network design. Choose architecture matching your problem's nature. Start simple and gradually increase complexity. Regularize and validate models to prevent overfitting. Use pre-trained models when available. Tips for writing clear Gen AI prompts. Be explicit about the network type and task. For example, generate a PyTorch CNN model for image classification with 3 convolutional layers. Specific prompts help generate practical code and guidance. Conclusion. Understanding feed-forward, convolutional, and recurrent neural networks is essential for building effective AI solutions. Each architecture serves unique roles with specific strengths and weaknesses. By mastering these, you can design models best suited to your data and goals. Thank you for joining this session. Begin implementing these architectures confidently to solve complex problems efficiently.